Dear audience, it's my pleasure to present this talk, Hydrogen-Assisted Cracking Paths in Cold-Drawn Pearlitic Steels, with the beautiful logo of the University of Salamanca, 800 years old, the oldest university in Spain. Two authors, Jesus Toribio and Elena Ovejero, with the Fracture and Structural Integrity Research Group of the University of Salamanca. The outline of my presentation into 5 parts: introduction, experimental program, experimental results, discussion, and conclusions. First of all, the introduction. The motivation: fabrication of high-strength persistent steel wires by progressive cold drawing produces a progressive orientation of the 2 basic microstructural levels of pearlitic colonies and lamella, and as a consequence, an influence on the posterior hydrogen-assisted cracking hack behavior. The aim of the work is to analyze the influence of the cold drawing degree on the hydrogen-assisted cracking performance of high-strength steel wires. This is a fracture mechanics approach to the design of pre-stressed concrete structures. There is a previous key question: is the cold drawing manufacturing process beneficial from the hydrogen-assisted cracking point of view? What about hydrogen-assisted cracking paths? The experimental program. Materials used: progressively cold-drawn pearlitic steel wires. The steel composition: eutectoid composition, roughly speaking 0.80% of carbon. Cold drawing consists on an increase of yield strength and ultimate tensile strength by a strain hardening mechanism, with progressive orientation of the 2 basic microstructural levels of pearlitic colonies and lamella. Here I am showing 2 pictures of a real cold drawing process of pearlitic steel to manufacture pre-stressing steel wires, commercial pre-stressing steel wires. There is a progressive cold drawing, passing of the pearlitic steel wires through several dies, and main consequence, this is the final aim of manufacturing, an increase of yield strength and ultimate tensile strength by a strain hardening mechanism. The stress-strain curves reflect this process of strain hardening, with a clear improvement of mechanical properties, yield strength and ultimate tensile stress, as a consequence of the cold drawing process. Here we can see from steel is 0, hot roll material that is not cold drawn at all, 1, 2, 3, 4, 5, 6, 7 steps of cold drawing, with increase of both yield strength and UTS. The evolution of pearlitic colonies, here for 3 levels, steel 0, 3, and 6, undergoing 0, 3, and 6 steps of cold drawing. We can see a progressive orientation of slenderizing of pearlitic colonies. They become enlarged, slenderized, and oriented in the vertical side of the slide, y-axis or cold drawing direction. With regard to the evolution of pearlitic lamella, ferrite cementite lamella for steel 0, 3, and 6, 0, 3, and 6 drawing steps, while in the steel 0 we have in the longitudinal axial metallographic section an isotropic randomly oriented microstructure. Steel 3 exhibits a more or less oriented microstructure, and steel 6 is like a microcomposite or nanocomposite with a marked orientation of ferrite cementite lamella in the y-axis or cold drawing direction. It's like a micro or nano-laminate ferrite cementite. The experimental program consisted on constant extension rate test or slow strain rate test, SSRT, on transversally pre-cracked rolls immersed in aqueous environment. The specimens were pre-cracked by axial fatigue in air with a maximum stress intensity factor, K max, equal to 30% of the critical stress intensity factor, or K1C, fracture toughness of the material. Two constant electrochemical potentials were used, E equal to minus 1200 millivolts SCE versus saturated calomel electrode. This is cathodic potential in the Pourbet diagram, promoting hydrogen-assisted cracking mechanism, and on the other hand, E equal to minus 600 millivolts versus saturated calomel electrode, anodic potential promoting localized anodic dissolution or pure stress corrosion cracking. Let's go to the part 3, experimental results. This is a plot representing F hack divided by F0. This is the load in a hydrogen environment, hydrogen embrittlement, hydrogen assisted cracking load, divided by the failure load in air. This is the vertical axis of the plot. This is the susceptibility to hydrogen assisted cracking in vertical axis, left, and another vertical axis, time to failure, time to hydrogen-assisted cracking in hours. In the horizontal axis, we represent the degree of cold drawing degree, represented as the ratio of di versus d0, the ratio from the initial diameter, from any diameter after cold drawing to the initial diameter d0 before cold drawing. What do we see in this plot? We see, with regard to the evolution of fracture load, we cannot observe any specific trend, but with regard to time to failure, there is an increasing trend. Here we discuss this plot. No significant improvement of hydrogen-assisted cracking resistance, represented by the load, F hack, load on hydrogen-assisted cracking situation, as a consequence of the cold drawing process. The fracture load under hydrogen-assisted cracking conditions does not strongly depend on the degree of cold drawing, the ratio of diameters. However, a certain drawing-induced increase of time to failure T hack, hydrogen-assisted cracking time to failure, seems to exist. The result is a slightly better hydrogen-assisted cracking performance in the cold drawn precision steel wire than in the hot roll bar, with a real increase of time to failure. With regard to crack paths, micro crack paths, or hydrogen-assisted cracking paths in the form of fracture profile, here we can see 3D views and profiles for different degrees of drawing. Slightly drawn steels fail in mode 1. After the fatigue pre-crack, there is a mode 1 propagation, subcritical cracking, and final fracture by cleavage. 0, 1, 2 degrees of cold drawing, and for intermediate degree of drawing, there is a slow propagation by mode 2, mixed mode, in hydrogen-assisted cracking subcritical conditions, and in the most heavily drawn steel, after fatigue pre-cracking, there is a sudden deflection angle of almost 80-90 degrees and fracture propagation in almost perpendicular direction to the initial one in mode 1 by fatigue. There is a strong component of mode 2 in this mixed mode and isotropic hydrogen-assisted cracking behavior. In the bottom of the slide, we can see these profiles with increasing deflection angle with the increasing degree of cold drawing. This means a progressively anisotropic hydrogen-assisted cracking behavior with cold drawing, with increasing hydrogen-assisted cracking path deflection angle with the degree of cold drawing. Discussion. With regard to the susceptibility to hydrogen-assisted cracking, there is a clear effect of hydrogen, so that for a slightly drawn steels behaving in isotropic manner in mode 1, we can evaluate the critical K in hydrogen embrittlement, hydrogen-assisted cracking conditions divided by K1C versus the degree of cold drawing, and there is a marked reduction as a consequence of hydrogen. It means a high susceptibility to hydrogen-assisted cracking in slightly drawn steels. This means risk of cathodic overprotection in civil engineering design of pre-stressed concrete structures. Cold drawing produced no significant improvement in the hydrogen-assisted cracking resistance of the steel in spite of the clear increase of yield strength in the material, final line of manufacture. This seems to be valid for heavily drawn steels. Previous research showed that the very high yield strength could be responsible for the marked susceptibility to hydrogen-assisted cracking. With regard to crack paths, hydrogen-assisted cracking paths, we see the picture of slightly versus heavily drawn steels in 3D view, increasingly anisotropic fracture behavior, and the fracture profile showing the crack paths under hydrogen embrittlement condition and the increasing crack path deflection angle with the degree of cold drawing in the presence of hydrogen. We have a progressively anisotropic hydrogen-assisted cracking behavior with cold drawing, reason progressively orientation of pearlitic microstructure with cold drawing at the two levels of colonies and lamella. Mixed mode cracking appears for a really low degree of cold drawing from steel 2, and crack deflection takes place just at the fatigue pre-crack tip, that is, with no hydrogen-assisted subcritical crack load in mode 1. Hydrogen promotes sudden deflection created by promoted by the microstructural anisotropy, but also enhanced by the presence of hydrogen. With regard to microcrack paths in the hot-rolled steel, the crack advanced by breaking the lamella, but in the cold-drawn steel, the crack advanced by pearlitic delamination. Going back, breaking the lamella means a mechanism of the hydrogen-assisted cracking by tearing topography surface, but in the case of cold-drawn steel, could be hydrogen-enhanced delamination or decohesion. Let's go to the conclusions. In eutectoid steels, the changes produced by the manufacturing process, cold drawing, in the two basic microstructural levels of pearlitic colonies and lamella affects the hydrogen-assisted cracking performance. The crack propagation changes from mode 1 in slightly drawn steels to mixed mode in heavily drawn steels, which means a progressively anisotropic behavior with the cold drawing process. While in the hot rolled steel, not cold drawn, the crack advances in a hydrogen environment by breaking the pearlitic lamella, in heavily drawn steels, the cracking mechanism is hydrogen-enhanced delamination or the bonding between two similar microstructural units, the pearlitic colonies or the ferrite cementite lamella, which is consistent with the anisotropic behavior and the mixed mode propagation in this kind of steel. Is longitudinal splitting or delamination or decohesion. In heavily drawn steel could be a HEDE, hydrogen-enhanced decohesion or delamination, while in slightly drawn steels or hot-rolled steels it is tearing topography surface more closer to the mechanism of HELP, hydrogen-enhanced localized plasticity, a kind of localized tearing, localized plasticity enhanced by hydrogen. Then we have HELP for slightly drawn steels, hydrogen-enhanced localized plasticity by tearing topographic surface, and HEDE, hydrogen-enhanced decohesion, delamination in the most heavily drawn steels in which the decohesion or delamination is produced in the lamellar, ferrite cementite lamella, or in the colonies, the bonding. And that's all. Thank you very much for your kind attention.